Log on, tune in, find out. Another good idea from Cambridge.
Okay, so I'm going to be talking about phylogenetic trees, which turns about will have something to do with Stirling numbers, not surprisingly. It should be actually a fairly short talk, so I will probably make up for time. So, counting trees, unordered trees, means that the way you draw it doesn't matter, has a large history. So I will define a species tree, but everybody knows what it is. But for me, a species tree is a leaf-labeled tree where the labels occur with multiplicity 1, meaning we are talking, we are talking about a species tree. The root is not of degree 1. This is a technicality. You may choose your root to be of degree 1, having that last edge or not, but you have to decide which one you are using. And for purposes of mathematical analysis, at least for counting and a couple of other things, I found it's much better for me that if I don't have the root of degree 1. And non-root, non-leaf vertices are at least degree 3 because they are speciation events. Mathematicians, so two trees are the same if there is an isomorphism between them, that also preserves and they look the same. In 89, Cayley had a formula for unleafed trees with n vertices. I should say they were labeled. And labeled means that all the vertices were labeled. Weatherburn and Etherington showed a functional equation for the ordinary generating function of rooted unlabeled binary trees. In 48, Otter showed that for unlabeled trees, that formula showed. That formula basically says that you count the number of different vertices. Two vertices are different if they don't look the same. You can't, and they are the same if you can't distinguish them from local information. So if there is an isomorphism, you take one and the other. Minus the number of different edges, plus the number of symmetry edges of which there is at most one, you get one. And this is an important equation because it is a way to relate rooted trees to unrooted trees. So if you have counts for one, you can obtain counts for the others. And he obtained asymptotic for rooted and unrooted unlabeled trees on n leaves. In 67, Cavalli, Sforza, and Edwards, in 74, Dobson, in 76, Phipps, and I may not know about everybody, gave a formula for rooted and unrooted leaf-labeled binary trees with n leaves. And Flageolet gave asymptotics for the total number of phylogenetic trees on n leaves, which is essentially Schroeder's fourth problem from 1870, and developed the program package construct, which is actually very useful to do these things because they involve huge computations that you don't want to do by hand. Absolutely not. So rooted leaf-labeled trees have to do with partitions. So some notation by F and K, I will denote the number of rooted leaf-labeled trees with K-labeled trees and N non-root vertices. So N, which is one of the important parameters for me, denotes the number of non-root vertices. And K is the roots. Importantly, what I'm talking about is mathematical trees. In a mathematical tree, the root may or may not have degree 1, and I will not consider it as a leaf. That's important for something else. Remain there, sorry, I stole these slides from somewhere else. And degree 2 vertices are not suppressed. So there can be internal vertices along the tree that have degree 2, which is from the biological point of view, doesn't really make sense. And the Stirling number of the second kind, Sn(j), is the number of partitions of an n-element set into j non-empty partition classes. Why do I talk about these? In 1983, Erdős and Székely proved that those two numbers are the same, f and k and Sn(n) minus k plus 1, using a bijection. And very importantly, under this bijection, all degrees of non-leaf vertices correspond to precisely the class size. And I want to use that later. That in particular means that if you have results, for example, the distribution of the Stirling number of the second kind, it also translates to distribution of those rooted leaf labeled trees. And in 68, Dobson showed that the Stirling numbers are unimodal, which means that they have a unique maximum. The Stirling number sequence is strictly log concave, which also implies that it's unimodal. That's all. Okay. So there are some normality results, but for that I have to say some more definitions. I have this sequence of finite sequences. That's what A and J is. The range of J is finite, and N is bit sequence I'm talking about. I construct this number E sub n by adding the A sub n's for all the range of J, and I create a random variable Z sub n by probability Z sub n equal to J is A sub n J normalized by sub En, by this En. This En is only needed to make sure that these are indeed probabilities, they add up to 1. By definition, this array, A and J, is asymptotically normal if that funky formula can be simply translated to if I take its standardized version, expectation 0, variance 1, the corresponding cumulative probability density, cumulative probability function, no density, actually converges uniformly in X to the cumulative density function of the standard normal. In 1967, Harper showed the asymptotic normality of the Stirling numbers, and he gave the expectation and the variance, which means that you actually can use this to estimate the Stirling numbers without having to go through a long recursion. In 1977, Canfield showed the following, that asymptotic normality, strict log concavity, and variance going to 0, these conditions together imply this slightly different formula. But this essentially means that if you take not the cumulative density function, but the probability density function of the normalized version, that goes to the probability density function of the standard normal, uniformly. So how does this method work? Because it's fairly simple, I'm going to describe it. We consider the generating function of the nth finite sequence up there. It's fairly simple to compute the expectation and the variance of the variable Z sub n from this. And if you can show that this generating function has only non-positive real roots, so all the roots are real and all the roots are non-positive, then the probability generating function actually can be written as the product of Bernoulli variable, the probability generating function of Bernoulli variables, which means that this variable Z sub n can be thought as the sum of independent Bernoulli random variables. The sum of independent random variables, under reasonable conditions, you would expect them to go to a normal distribution, and indeed they do if the variance go to infinity. The Lindeberg-Follett theorem implies. And by Canfield's lemma that I had on the previous page, if I have all this, if I also know the strict log concavity of the sequence, then we have that locally kind of conditions too, which is somewhat stronger. In order to do this, we have to know what the Stirling numbers sum up to, and they sum up to the Bell numbers, which is the number of partitions of an n-element set. And in 1955, Moser and Willem provided asymptotics for V sub n. I should say that they were, to my knowledge, the first one who provided it correctly. A couple of other people have published results on this previously. That's why the programming package is that important, because the computations are just forbiddingly hard. And in 1994, Campbell provided this formula, which is an extremely important tool, because what happens here is that when you want to compute the Bell number around some quantity n, B sub n plus 1, and so on, this only depends on n. And R, which is the solution of this equation, is called the Albert function. And that means that you can actually fairly easily estimate things that look like b sub n minus 1 over b sub n plus 5, where the differences are constant without having to go to any sort of big trouble. And that's very important when you want to do this calculation. So how does it work? And R is of the order of log n times log n, and you can extend it further. So how does this work? This is still not. This is for n equals to 15, the distribution of S15K. Obviously, it's just smoothed and the dots are the actual data point. And if I use the expectation, the variance, I would fit on it the normal curve. This is what we get. Fairly good fit. But this is not what we want. These are just mathematical trees. These are not the real trees that we are interested in. So let's think back to the average state bijection. Our degrees of non-leaf vertices correspond to class sizes. Now, if we have a phylogenetic tree the way I defined it, and I made sure that the root is not of degree 1, then being a phylogenetic tree means that the class sizes are at least 2. That's all. So I will denote by S star the corresponding version of the Stirling numbers. Number of elements is n, number of partition classes are k, and I have the restriction that each partition class has size at least 2, which means that the range of k is between 1 and n over 2. And the corresponding total number of partitions is bn star. And F star n is the number of leaf-labeled trees where you have k labeled leaves and n non-root vertices. And I have the restriction that odd degrees of non-leaf vertices are at least 2. These are of phylogenetic trees. These are exactly of phylogenetic trees. And since the average CK bijection, I still have this formula between the star versions. So we have to have some access to these B star numbers, and it's fairly easy to do that Bn is Bn plus 1 star plus Bn star. It's actually a simple exercise for your grad students if you want to make them do something in the beginning when you make them learn this, from which you can obtain this formula, and estimations of Bn can be used to estimate Bn star. You can show that the expectation and the variance of the corresponding random variable are these formulas. You could go further if you wanted to make Maple a little bit more, having a little bit more sweat, but it's a very long computation. And it does involve a little bit of tricks with that Camfield formula before you can do this. Now we have shown that the star version is asymptotically normal, and also it has the local condition that I mentioned earlier, for which you need to show that it's strictly log concave. The generating polynomial has different non-positive real roots, and the variance go to infinity, which is fairly obvious from the formula, since R is of the order log n. But what does it mean? This means that if we fix the number of non-root vertices, that's my n, and count the number of trees with k internal vertices, the resulting distribution tends to normal. So how does this look like? Use the same n15. S star 15k is a tree with 16 minus k leaves and k internal vertices. This is pretty much the corresponding distribution. Left are the dots. And this is the fit that we obtain. It's not quite that good, but let's go a little further. 15 is after all small, and then if you notice, in this case, the range has been reduced. The previous range was k had 15 different values. Now it has only 7. The 8th one is already at the 0. So let's make the range compatible. That means we get 31 minus k leaves and k internal vertices. This is my picture, and this is my fit. It's much better. It seems to work. But if you paid attention, you realize this is still not what you are interested in. Because what you would be interested in, fix the number of leaves. The number of leaves are not fixed. But that's not such a big problem. Number of leaves are fixed, number of leaf points vary. That's what I want to work with. That's the notation, Tn plus 1n. There is a reason I put the Tn plus 1 because formulas work out nicely. Denotes the number of trees with n plus 1 leaves and n internal vertices. And you can translate it to that. The first thing, if you are a mathematician that you want to ask, what happens if I consider the unstarred version of these? The problem is that if I consider the start version, then the range of n is between 1 and n. I have finite a sequence of finite length sequences. In this case, I have a sequence of infinite length sequences, so the question doesn't make sense. So I can forget about this. We can do the same thing. Here's the expectation, here's the variance. I have to mention that Flageolet already doing the expectation only computed this much, because that's what he was interested in, but because we are interested in distribution, interested in precision, we went further. So how does it look like and we have shown that this is asymptotically normal and has the local limit condition by the same method. This is the distribution for n equals to 15, which means 16 leaves, number of internal vertices vary. This is the fit. But I didn't say that they are distribution with this. I said that it goes to. So what happens if I go to the other case n equals to 30? So 31 leaves, k internal vertices, the fit is much better. So the convergence is a bit worse here, but it works. And that's all I have to say, because otherwise I would have to talk about proofs, and that would be a bit too hard.
Thank you. Questions? Yes, Anna.
These, you've made the roots have a degree of vertex not 1?
Not one.
So that means that it's exactly a rooted tree from my perspective.
Yes, but you can
We're
make
sure
it
about
exactly
that.
degree 1 or exactly non-1, but you have to make a decision. The two things are equivalent.
But they're exactly the same because you fix it, right?
Okay, if there are no more questions, then we should thank Eva again.